Thank you very much for the introduction, and let me go right away to the contents of my talk. So, RICEN is a supercomputing center. So many people may question what is a future way where quantum computation will merge with supercomputation. And there are essentially two ideas. The first is that the existing machines at the supercomputing center may be used to simulate quantum mechanics. And this is using their multi-GPUs, the multi-node or TPUs, future TPUs, to do a simulation of a complicated problems, like finding the structure of some molecule. But there is a second way of doing quantum computation merging with supercomputing, which is to think that the supercomputer simply is assisted by the quantum processing unit. And this is typically referred as a hybrid computation. So what I'm trying to do today is not talking about simulation. I will not be discussing how to put a quantum mechanical problem in a supercomputing, but rather I will try to tell you, the audience, what are some of the ideas behind quantum computation itself. So I will be very, very basic, starting from the beginning, and I will take some introduction to make it clear that writing a quantum algorithm is not trivial. And then I will move to the so-called variational quantum algorithms. So let me go through that. So the quantum computers are here. As you know, there are a number of computers of 50 qubits. And the first large contracts are there. So this is now a reality. It is often said that these computers are not good enough for any practical use. And this is why people are using the term noisy intermediate scale quantum era, the NISQ era. Even in this NISQ era, it is not easy to program, to write a quantum algorithm. Let me tell you why. Well, let's go back to basics. The idea of a quantum computer is that we go down to the fundamental elements of nature, and imagine here you have a spin, and I represent that with an arrow. And in that spin, I act with a magnetic field. So according to the laws of quantum mechanics, I can represent the basis of the spin as a 0, as a 1, a spin up, spin down, for instance. And then I may have a magnetic field that simply goes halfway between 0 and 1. This is quantum mechanics. So we can generate what we call superposition. And I'm representing that as what I call a Hadamard operator. And this is a unitary operator that takes 0 into a superposition of 0 and 1. Or you may have the interaction of the spins, and you can tune them in such a way that you have a C0 gate. So some of the gates, as you see, maybe in quantum mechanics may be identical logically to the classical, but other gates are completely new, like the Hadamard. There is no such a thing as a minus sign when you use quantum mechanics, classical physics. So the minus sign that you find in the Hadamard gate is a genuinely quantum mechanical idea. And this is the origin of interference. So eventually the amplitudes of the states will cancel because of the minus signs. And this is why quantum computation is so different from classical. Yet it is true that when you have a state, you have 2 to the n complex numbers to describe the state. So a quantum computer of n qubits is representing 2 to the n complex numbers. And this is really impressive. Not only that, but if we take an action on the state, this action is done in parallel over all the superposition. This is why many people claim that the quantum computer is a massive parallel computer. But this would be an oversimplification, because the laws of the kind of things you can do are not the same in the classical world and in the quantum world. So let me give you examples of things you cannot do with a quantum computer. The first is the naive idea of multiplying. So I have 2 registers. I have a register with 1, 1 that represent a 3, and I have another with a 2, 1, 0. And I ask myself, what is a quantum secret that would deliver a 6, a 0, 1, 1, 0? And this simply does not exist in nature. The reason is that the evolution that we have to use, the basic laws of physics, are unitary, okay? So that means that they are reversible, they are invertible. But you see, if I'm giving 6, there is no way I recover 2 and 3. It could be 1 and 6. So how does this work? There is no way to write a unitary evolution that is a multiplication. Instead, what we need to do is to have always memory of the first state. So we may build an operation that takes 2, 3 and sends it to 2, 6. But then we have the 2 always. And the 6 is related to the 2. And this is the origin of entanglement. So if we set a superposition of operations, all of them then suddenly become entangled. So you see, it's much more complicated than you would do in the classical world. In a similar way, we cannot copy a register. So we ask ourselves whether we have an ancillary register that you call 0, and I want to copy any state, let's say 2. Is there a machine that copies any state? In this particular case, 2, 2. So is there a cloning machine? And again, this is not possible. Why this is not possible is more sophisticated. You have to do a little theorem, and the theorem goes as follows. You may take a 0 and copy it into an ancilla that you prepare. Think of a copy machine, a white paper, you copy the 0, or you may copy the 1. But then if a superposition comes, you will never copy the superposition. You are missing all the cross terms. So there is a fundamental obstruction to cloning. There is no possibility of saying A equal to B and then proceeding with A and B in your memory. That means that the art of writing a quantum algorithm is far from obvious. Not only that, but there is even another difficulty, which is that when you finish your computation, whatever the final result is, and I measure, I will only get a probability. So all outputs are possible, but with different probabilities. So actually, a quantum machine is only generating a probability distribution. And we have to tune these algorithms so that the probability distribution provides a solution to the problem we are interested in. So this is, as I said, far from obvious, yet there are examples of success. Let me give you the first example. This is the so-called oracle problems. And here I put the picture of Delphos, the famous Greek oracle. The idea is substantially trivial. It's simply going there and asking a question and getting an answer. So I ask X and I get f of X, but I have no idea how f of X was computed. It's a complete mystery. It's an oracle. I simply ask X and I receive f of X. So the question is whether a quantum computer could help here. And more precisely, what about sending a quantum state that I represent as ket of X, and I receive the unitary evolution that the oracle will implement on that state? Can I do something better than the classical? And indeed, the example is the following. The simplest possible question that we may ask is whether the function only receives an input which is a 0 or a 1, a bit, and it only delivers a bit. So it's f of 0, f of 1, and it may be 0 or 1. So it's an application of 0, 1 into 0, 1. And there are only two possibilities, that f of 0 is equal to f of 1, or that f of 0 is different from f of 1. So if I put 0 and f of 0 is equal to f of 1, I get 0. If I put 1, I get 1. In the other case, if I put 0, I get 1. If I put 1, I get 0. So the question is, can I decide whether f is balanced? And it is clear that classically, there is no other way but sending the 0 and the 1, receiving the f of 0 and f of 1, and then checking whether they are equal or not. So I need to call the function twice. Yet, quantum mechanically, Dodge and Josa, many years ago, invented this quantum circuit. And it is a remarkable circuit. It shows the power of quantum mechanics. You simply put the 0 and a 1. You start your circuit with 0 and 1. You do 2 Hadamard gates, the ones I mentioned in the beginning. And line by line, you see how it acts there. So I put 0, 1, and the second line, you see 0 plus 1, 0 minus 1. Then I act in the oracle in the way I show with the multiplication. So if I have a 0, on the other, I have 0 plus f of 0. If I have a 1, I will have whatever plus f of 1. And then you simply combine this output, and you suddenly see that in the very final stage, I can read a 0 or a 1 on the first qubit at a condition, which is 1 plus minus 1 to f0 plus f1. So if the two functions are identical, if the two outputs are identical, this is a constructive addition. And on the other hand, the second term is a negative addition and therefore 0. So you see, it's by canceling of amplitudes that finally, in a simple measurement, if I measure 0, I know the function is balanced. If I measure 1, I know the function is not balanced. So instead of 2 calls, I only need 1. In general, to know the origin of f of x given y, so I need a total of a square root of n calls rather than n calls that you would need in the classical world. This is the so-called Grover algorithm, and it is one of the primitives of quantum computation. And I insist one more time, all the effort that is done in quantum computation is related to the correct combination of the amplitudes. So that the state will always be normalized, so the addition of the square of the amplitudes must be 1. But the art of writing a quantum algorithm is to transfer amplitude probability from one particular final state to another. This is represented in a different way now. I'm simply writing for the record how this Grover algorithm works, square root of n actions, and each of these actions is made of 2 steps. One is the call to the oracle, the other is called a diffuser, is U of S. And little by little, these actions are driving the original state into the solution. And the way it works is by doing a very clever trick. The amplitude we are looking for, the state we are looking for, simply changes sign, and that it modifies the average. The dotted line is the average. And the diffuser manages to do an inversion around the average. And this is what it is being the hardcore idea of transferring amplitude from all the other states to the one which is a solution. So we are little by little transferring probability amplitude. Let me also mention, and I will not present it, that the big success is how to transfer probabilities in a register in such a way that we solve a factorization problem. In particular, what it does, the famous algorithm by Shor, is to find the period of a function. Take A, any number to R equal 1 mod n, find R. This is the hardcore idea of Shor's algorithm, and it is achieved by the so-called quantum Fourier transform. Again, when you finish your result, you see that what you've managed is to transfer probability amplitude from all the possible outputs to the ones that are on a set of points that provide the information about the period. Okay, so this was the introduction. I know that many people have read about Shor's algorithm, and many people have read about Grover's algorithm. They remain, as of today, as the 2 most important primitives to address problems with a quantum advantage. Okay, this is a fact. But as I said, we are now thinking of how to use quantum computation for beyond these two ideas. Okay, and basically, you could divide all the efforts to write quantum algorithms in three categories. The first category is the one I'm showing you till now, is a gate circuits where we know exactly what to do at every step. This is the search by Grover. This is the quantum Fourier transform. This is the Dodge algorithm, just a Dodge that I showed. The three examples I show are on the left. They are the gate circuits where we know exactly what are the gates. But you may have heard about annealing. So this is a quite different philosophy. Simply thinking that if we codify the solution of a problem as a minimum energy of a particular interaction in nature, well, nature itself will try to go to the minimum energy state. That's annealing, okay? So we don't know how to get there. We hope nature does it for us. There are two ways of doing that, direct annealing and adiabatic evolution. And there is a machine that does that, and this machine is D-Wave. Let me make it clear that D-Wave operates as of today in times that exceed the coherence time. So it is less quantum than expected. Yet the results are not that bad. So it is foreseeable that we will make big progress in annealers, and annealing will be one of the mechanisms to solve problems. The third category are variational algorithms. So the idea here is whether we can learn from artificial intelligence, all the technology of machine learning, to encode, to get quantum circuits that provide the solution to a problem. So we want to mimic artificial intelligence, but now with a more powerful engine, which is a quantum computer. Let me briefly say why this is a clever idea. The idea is that we don't know how to program a solution of a very complicated problem. Yet we have the quantum computer. So we can operate, we can do gates in the quantum circuit. I don't know which are the gates which are necessary, but I ask myself a preliminary question. So if I write a circuit with all these gates, given a set of fundamental gates, can I tune them in such a way that I go to a particular state? So is it possible, on the picture on the right tries to show that, is it possible to have a path in the Hilbert space that will bring me close to the solution I'm looking for? So the question first is whether a circuit can represent any unitary evolution, because there is a unitary evolution that will take from any state to any other state. But can I do it with gates? And it is very fortunate that we do have a theorem, which is called the Solovay-Kitaev theorem. And it says that given a set of unitaries, of gates, which are a dense set, it turns out that if I want to approximate another unitary, a V unitary, I have a circuit that goes from U1 to UK, so K operations. And I ask myself whether I can be close enough with some measure of distance in the space of unitaries. So the theorem shows that indeed this is possible, and that the scaling of K, the number of gates I need to achieve a given precision delta, only grows as a log to a given power C. So that means that given a problem and given a set of unitaries, increasing the accuracy of my circuit to describe what I want to describe, which is this V operation, is not an exponential effort. It's only polynomial. It is true that the coefficient in front of this K, it's exponential in the number of qubits, but the increase of accuracy is not. So that means that if we can handle a problem in a quantum computer, adding the gates, I will not need an exponential number of them. It's a pity that this algorithm does not give us the construction that we need. So it is just a theorem of existence. Now, this was for the first time presented by the group of at IBM, by Alan Aspuro-Guris and all the team. And what they did is the following. They describe a quantum secret with gates. They read out random state. They check whether this was the energy of a molecule. And if not, they went with machine learning techniques to the secret and modified the secret till the energy was going down little by little. So if you look at this, it's very similar to a neural network. You have a neural network, you have a chi-square, you have to minimize the chi-square. If it doesn't work, I modify my weights. Here you have a quantum secret, you have a readout, you have a chi-square. If the chi-square is not good enough, you modify your secret. And that idea was put forward and implemented in a quantum computer. And this was the first time we had a hybrid classical quantum algorithm. And it was applied for the molecules of hydrogen and then several molecules. So it worked. Okay. There are many unexplored options nowadays on this philosophy. First is how you encode the data, how you process it, how do you read out. You have so much freedom there that people are simply exploring what is the best possibility. The standard way of approaching is that the quantum secret is organized as layers of gates, which are single qubit gates and then entangling gates. This is what people are doing. And every time I have a layer, I increase the versatility of my model. I can describe a more complex probability distribution. If you apply this technology to solve a Hamiltonian condensed matter problem that we did, you can see that the number of layers is dictated by the amount of entanglement you find in the state. So in this graphic, you see the precision on the horizontal line. The more you go to the right, the more precise your description is. And on the vertical line, the depth. So as you see, if you increase the number of qubits, change the colors, you need more depth to describe the same accuracy. But little by little, after you have done a number of layers, suddenly the precision increases dramatically. Okay, this is the idea that first your quantum secret needs to understand the entanglement needed in the state, and then precision comes. Okay. Let me now move to apply the idea of variational quantum algorithms to different problems. One is a classifier. So what I will do is the following. I will try to put, with an example, things are much easier. I want to classify the points on a plane according to whether they are inside or outside a given geometrical pattern. So in the left, I want to understand whether the points are inside the circle or outside the circle. So a way to do that is the following. I put the x and y as a vector, x, and I have variational parameters I call alpha. And when I put them together, this defines a unitary, which is a rotation for the qubit. And one by one, I keep doing that in layers. Now, the layers are very simple because this is a single qubit. So I can put several layers, and little by little, as I see in the table, the more layers I have, the more precise my classification is. So I repeat it. I start with 0. I do a unitary where I have the data point I want to classify combined with variational parameters, and I do that several layers. I train the variational parameters as if they were the weights of a neural network, and finally I read out. And if it is close to 0, I declare it is inside the circle. If it is a 1, I declare it's outside the circle. And with that technology, I can do a classifier. This can be extended to multi-classes, as you see on the right, and it can be extended to several dimensions. And you can even see how when you add the layers, you start to set regions in the space you are classifying. So here on the left is what is the classification. On red and green is success and mistakes. And as you increase the number of layers, you see how little by little you are defining the regions till finally you have a good classification. These 6 layers have the same accuracy as a neural network with one hidden layer of 100 neurons. This is the accuracy you get. We did that. And what you see here is a classification again of zones, but now the figures are not theoretical predictions, but rather experimental results. Okay, this was done using an ion trap by Professor Mukherjee, and it works with 4 layers. The accuracy finally is not bad. It's 96% accuracy. So indeed, this is an example of a real quantum classifier. So it's really done by quantum mechanics. Why is this working? Well, the key element was to, in every layer, add the data. So you see, you are re-uploading the data in the different operations. It's very similar to a neural network where you re-upload the data in every intermediate neuron. So at stake, what we have is this idea of query complexity. How many times I made a query to the data I want to classify, and then I put them in different places. This is really what is at stake. So is this something we can formalize in a more rigorous way? Indeed, this is to understand that just 1 qubit is already a universal approximant. Let me show you that. The idea is whether I can build any function, z of x, and that I know I can do it with a Fourier series. And the more terms in the series, the better the accuracy I can get. So can I mimic any Fourier series with a quantum circuit? And indeed, if I take the structure I was showing before, I can see that 1 gate is simply a combination of rotations. And here x enters, as you can see, in one of the rotations, and all the other angles are put there at will. And then a circuit is a product of these gates. And I simply recombine all these data into the matrix below. It's simply exactly the same thing as above. And then I see if I add 1 gate, what happens to the circuit. And by induction, what I see is that indeed, if it was a Fourier series, the next term can be described by the combination of the new gate and the previous ones. So indeed, this series of operations form a Fourier series. Okay, you can also prove the opposite, that any Fourier series can be constructed at this set of operations. So that means that a single qubit with a re-uploading of n gates is a Fourier series of size n halves. Okay, and indeed, again, we did the experiment in 2020, and we were reproducing here with 2 4 layers arbitrary functions. And here you see step functions of different kinds, and indeed it works. So the morale is that the quantum computer, with a single qubit, is already a universal approximant. Let me give you a few other examples of what you can do with variational algorithms. This is a little bit mathematical, but again, I'd like to present it. You will see why. You may know that one of the main things we need in quantum information is the so-called singular value decomposition. That's a diagonalization of the tensor. So you have a tensor T that describes a ket, and I simply want to diagonalize it with 2 unitaries. So I have U and V acting on the subspace, Hilbert subspace A and B. And the question is whether I can make it diagonal. There is a theorem that says that this is possible. And this is the so-called Schmidt form of the state, or tensor. But the question is how you get it. Well, the Hilbert space has an exponential number of elements in the basis. So this task is exponentially hard. Okay. If I manage to do it, I have a lot of information about the state. For instance, I can compute the von Neumann entropy with the eigenvalues lambda k. Now, how can you do that? Well, you can do it with a variational secret. And to do that, let me show you that what you can do is the following. You apply two distinct unitaries to Alice and Bob part of the register, and you train the variational parameters theta and omega in such a way that the outputs are systematically identical. This is possible by theorem, and immediately you see that then you are going to the form of the state, which has the eigenvalues and then the computational basis there. So by variational approximation, by machine learning, you are diagonalizing the matrix. Okay, and this can be shown, and you can check that this works. Why I like that is that the other way out is really to measure the state, all the components, and this is tomography, and this requires 4 to the n measurements. Okay, whereas here you're always measuring the single computational basis, and you get the result. Let me go to another example, an autoencoder. Autoencoders are very common in machine learning, and the idea is that you want to find a relevant subspace, a latent subspace. Can you do that with a quantum computer? Again, you can do the same thing. So look at the bottom drawing. The idea is that we have a secret, which is variational. We are given inputs, and we force the training of the secret to get a 0 on the first 2 qubits, for instance. And then, if I want to invert the thing, I simply have to put 2 ancilas at 0 and do the same secret that managed the compression, but now taking the adjoint. Okay, so it's exactly the same thing as you do with neural networks, but now with a quantum secret. And when you do that, indeed, you can do it. For instance, this is an example of doing that with introducing eigenstates of the Ising model, and how you take a combination of 2, you don't know which, yet you can build a quantum secret that compresses it to a single qubit, and then you can do the adjoint and measure the fidelity. And as you increase the number of layers, the fidelity increases. So you are getting a better and better autoencoder. It's quite a very nice way of compressing quantum data. Okay. Let me say that all the variational quantum algorithms have a problem. Okay. If you look at the literature, if you look at the archive today, you will see that most of the papers deal with the same problem, the so-called barren plateaus. It is that, yes, we have a quantum computer. We can modify it because the parameters of the quantum computer can be treated variationally. But it may well happen that finding the good parameters that describe the solution is hard. So actually, we are transferring the difficulty from solving the problem to the difficulty of finding the optimal set of variational parameters. And this can be seen as a plateau. So finally, my parameters, if I change them, the output changes very little, and I don't find gradients to go down to a better chi-square. These barren plateaus are very old. They appear in many, many places. It's an issue related to both the problem itself and to the architecture of the approximation. There are plenty of ideas how to move away. In some cases, you can do it by changing the architecture of the quantum circuit. In other cases, you are facing an NP-complete problem. So therefore, there will be no way out. There will be no free lunch for this technology. And finally, let me use my final minutes to go back to the gates and see other ideas that we may explore. There is one that I love, and I will show you now, which is related to finance. So I want to do an option pricing. You may remember that the way the most trivial problem is formulated is as follows. So you have an asset that has a value of time t, and this value of this asset changes in time. And it changes according to an equation that it is stochastic. So you have a term which is at the Reddit, it's a deterministic change, plus a stochastic term with a volatility. Okay. Yet you want to compute the average value of this asset at the maturity time. And if that asset has a value which is larger than a strike, then I'm making profit. If not, I'm losing everything. So I have to do a sum condition to be this value, this maturity time value higher than K. I have to take this average. That's a way to compute the expected payoff. How do you do that? Well, what people do is a Monte Carlo. So you simply simulate the stochastic process. And when you take 10,000 evolutions, I have a probability distribution at maturity time, and I compute my averages. This is one of the problems that consumes more energy in finance, okay? Because by law, all the banks have to compute the risk for their clients. So if we find a way out here, that's a big thing, okay? In general, forget about finance. Anytime we can substitute a Monte Carlo by any other approximation, which is more efficient, then we are perfectly in good shape. So the idea here was to represent the value of the asset as a qubit, which is excited or not. But only one is excited. So that means that we are dealing with a unary representation. And that finally, as you may see here, the Monte Carlo simulations amount to a superposition of these unary values. And the probability then finally should be proportional to the probability we are looking for. This can be done by a circuit that distributes the probability. Another piece computes the expected payoff. And then we may use amplitude amplification to improve the square root of the speed, of the classical speed. And this, the detail of the distributor is the one you see, and the way you compute finally everything. You can compute it like that. And by reading one is when you read the payoff. And I'm showing this because of two facts. First, that in the short term, the scaling of this unary representation is much better for a small amount of pins. In the long term, unary is not efficient, but in the short term, unary needs much less pins than binary. And the error correction, because it's unary, if there are errors in your register, you can discard that very easily. So the reduction of error is amazing. And this is what we need in the NISQ era, reduction of errors. Okay, so this is why this is good. And let me also mention that this has now been implemented by the National University, the Nanyang Technological University of Singapore. And this is indeed a quantum circuit that generates single photons on the left. It has all the distribution of probability amplitudes. And in the very end, you have single photon detectors, and they are tuned. Everything is linked in such a way that you're computing the payoff for finance. So indeed, I like this because it's showing that you may have something that people don't talk about, which is a special purpose quantum computers. And we may devise quantum computers that only do one task. In this particular case, it would be a Monte Carlo for finance. And let me finish saying that for all the people that may be interested in starting to work in quantum computation, I know it's a stiff challenge, but at least you don't have to program everything from scratch. We have been developing a quantum operating system. So that is a language that links to the hardware and to the queues and to the diagnosis and benchmarking and optimization of the qubits, and also contains libraries. And this is an effort to be open source. So the idea is that we want to have a solution which is completely open source. We are now working from people from at least 7 countries, and this Kibo operating system will now be controlling 4 quantum computers in different countries. So we hope that the idea of open source will little by little enter. Singapore in particular has completely embraced the idea, and all the Institute for High Performance Computer joins the effort, and the National Supercomputing Center will have a quantum computer running on this open source operating system. That will also contains a cloud access, definitely. And that's, I hope this was interesting for you, and I finish now in case there are questions from you. So thank you very much.